Hello everyone and welcome to my YouTube channel. I cannot believe I am already making a video for year 11 this year, but hopefully this is not a common occurrence. But anyway, I thought I made this video to go through the content that you need to do for today, just because there's a couple of things that I think is a little bit harder to clarify just in writing. So I'm going to start by just having a quick recap of ionic compounds, which is the topic this week. So, as the name suggests, ionic compounds, first of all, is a compound. So, it will contain two or more elements, and it is ionic, which means that the elements exist in the form of ions in the compound. So, you will have cations and you will have anions. And for the most part, you can recognize that something is an ionic compound if it contains metal and non-metal. There's some exceptions to that, and I think I'll show you a couple of exceptions, maybe just one today. But for the most part, if you look at a compound, and you can tell that it is a compound because it has more than one element symbols in the formula. But if you see that one is a metal and then another is a non-metal, you can tell that it is an ionic compound. Next week, we're going to look at another type of substances. It's covalent compound. So you need to be able to distinguish between ionic and covalent then. So an example of an ionic compound would be something like sodium chloride, which you've seen last lesson. So sodium is the metal, chloride is the non-metal, but you can have a lot of other ones like KMnO4, for example, is one that you're going to use next semester. It has actually two metals, so there's potassium and manganese, and then oxygen is the non-metal. So it is important that you can recognize whether or not an element is a metal and a non-metal. You can use a periodic table for that if you're not 100% sure. So if you look at a formula and you're not sure whether something's a metal, check the position on the periodic table, and that normally helps. So that's ionic compounds. Obviously, last lesson we also looked at the ionic lattice and using the ionic lattice to explain some of the common properties of ionic compounds. I'm not going to go over that again. We can talk about that next week when I'm back. So the focus of today's lesson is looking at the naming and writing formulas of ionic compounds, which I think some of you, actually all of you, would have seen in year 10 science. This is should This should be a recap for the most part, and then there'd be a little bit of extension, I think. But if you've forgotten it all, then this is your chance to learn it again. So an example of the name of an ionic compound, so sodium chloride is the name and the formula is NaCl. So if the question is asking for the name, you have to write it out, and if it's the formula, then you're using the element symbols. I do want to point out the fact that an ionic solid is a lattice and not a molecule. So when the formula is NaCl, it doesn't mean that you're going to have one Na combining with one Cl. Like, this is not how an ionic compound exists, in solid form anyway, so make sure that you don't draw it like that. NaCl is just indicating the ratio between cations and anions in the lattice. So if the formula is NaCl, it's the same as 1 Na for every Cl. So the subscript is 1, it's just not shown. So that's just an indication of the ratio between the cations and anions, not an indication that this exists as a molecule or something like that. So it's actually a lattice, which hopefully you remember this from last lesson. Okay. We're going to make a comparison between this and the other substance that we're going to learn next week, which is actually a molecule. But an ionic compound is not a molecule. It's very important to remember that. It's a lattice. So this is the agenda. We're going to look at the naming and writing formulas of ionic compounds, so 4.4 and 4.5. And then before that, we need to look at octet rule a little bit as a way to predict the charge of some ions for some common atoms. So that's 4.3. So I'm going to start with 4.3. You can use this as the heading. So we're predicting charges of ions using the octet rule. And I think some of you have heard of the octet rule in the past. You can think of it as a very simple way to predict the charge of an ion, of an element, and it really only applies to some atoms. So it doesn't work for every single element, but it works for, I think, some of the main groups. This is the octet rule. So oct just means 8. So the octet rule reasons that atoms would gain or lose electrons in order to achieve a full outer shell of 8 electrons. So based on this rule, you can predict what kind of charge of an ion an atom is going to form. It is important, as I just mentioned earlier, it is important to remember that the octet rule only applies to main group elements. So main group elements, we're talking group 1, 2, and then 13 to 18. You cannot use the octet rule for transition metals, but then also, if you remember, hopefully, it's very difficult to work out the number of valence electrons for the transition metals, so it is a little bit harder already. And the octet rule really doesn't apply. You can have a transition metal that can form two different ions, or you have multiple transition metals that form the same type of ion. So there's actually no simple way to predict which ion a transition metal will form. I would have to tell you, and it has been known from observation and experimentation, but it is not something that you can necessarily predict. All right, so how do we use the octet rule for the main group elements? So we're going to ignore the transition part, okay? You cannot use the octet rule. But with the main group, you basically just need to apply the rule based on the number of valence electrons. So group 14, now group 14 has 4. This is 14, this is the old Roman number. Group 14 has 4 valence electrons. So if you want to go to 8, you technically can either gain 4 or lose 4. So what actually happened is that they will do neither. They actually will form covalent bonding instead. So we'll talk about group 14 next week. So group 14 doesn't really form an ion because it really can't decide whether it should gain 4 or lose 4. Now group 18 has 8 valence electrons, so it doesn't actually form ions. And then you have the rest. So group 1 has 1 valence electron. So it's going to form a 1 plus ion. So it's just going to lose that electron. Group 2 has 2 valence electrons. So the quickest way to get a full shell is to lose those 2 electrons. So it's going to form a 2 plus ions. Group 13 has a 3 valence electron. So it's going to lose 3. It's really just aluminium that's going to do that. I mean, some of the metals underneath as well, but aluminium is the main one that we're going to look at. Boron's interesting. Yeah, we'll talk about boron. Actually, I don't think we'll talk about boron at all, but boron is quite interesting. Group 15, it's going to lose 3. Sorry, not lose 3. Group 15 is going to gain 3 electrons. It's going to form a 3 minus ions because group 15 has 5 valence electron in the first place. Group 16 has 6 valence electrons, so it's going to gain 2 extra electrons to have a 2 minus ions. And group 17 with 7 valence electrons, it's going to gain 1 extra electron to become a 1 minus ion. So I do expect you to be able to predict the charge of ions for elements that are in group 1, 2, 13, 15, 16, and 17. Okay? I'll show you an example. So this is a question that you might be asked. Propose the formulas for the following ions. So if it is sodium, you just need to find where it is. So sodium is group 1, which means that the atom has 1 valence electron. So if we follow the octet rule, the atom is going to lose that valence electron to become positively charged. So the formula of ion will be Na plus because it has lost 1 electron. Calcium is in group 2. So calcium has 2 valence electrons. In order to get a full shell, the atom is going to lose those 2 electrons, so it becomes 2 plus. Barium is also in group 2. So also lose 2 electrons, become 2 plus. Now, when you have something like gold, and hopefully you can tell that gold is a transition metal. So something like gold, you can't actually predict the charge of the ion using the octet rule because of where it is on the periodic table. So if I give you an element like this, I actually will tell you what the charge is, and you can tell here. So the charge of the element, it's normally indicated by a Roman number here. I've been told that some people don't know how to read Roman numbers. I hope you can do 1, 2, and 3. It's pretty obvious, hopefully. So if it's a 3 here, then it's going to be a U3 plus. So if you have a transition metal, then normally in the name, the charge of the ion has to be indicated because you can't actually work it out either way. So this is another example of that. So we have iron 2 ion. So iron is Fe. It's a transition metal as well. So the name has to sort of tell you what the charge is. And then F is lithium. Lithium is also in group 1. It's a main group element again. and it has one valence electron. So if it loses that valence electron, it's just Li plus. So that's an example, okay? Now, another thing that you don't have to remember now, but hopefully by the end of next year, you do remember some of them, are polyatomic ions. So as the name suggests, polyatomic ions are ions that contain multiple atoms, so poly just many. And for now, I'm going to give you this table. So you really want to use this table for every question for this topic, and you're going to get this table for your next assessment. But I think eventually you want to memorize like some of the main ones from this. So this table gives you the name and the formula for some common polyatomic ions, so cations and anions. So for example, we have ammonium, and it is a polyatomic ion because you have one nitrogen and four hydrogen in the ion, and the whole thing has a charge of positive or 1 plus. And then you have something, and I think some of these, the script, like I'm not really a fan of because I think it's a little bit hard to see. But it's important to remember that the charge indicated in this table applies to the entire ion. And sometimes I think it's a little bit hard to distinguish between the number of atom and the charge. So for example, hydrogen sulfide, like I don't particularly like this writing. I got this straight from the textbook, but I think the script could have been written a little bit better. So HSO3, and then the whole thing has a charge of 1 minus. That's basically what it is. So it's important to be aware that this table exists and refer back to it when you do questions, because I think for some of them, I don't expect you to know what they are. Okay. All right, let's talk about 4.4. So two skills. 4.4 is naming ionic compounds, and 4.5 is writing the formulas for ionic compounds. So we're just gonna look at the names. So if I ask you to name an ionic compound, I will give you the formula first. Generally speaking, each ionic compound name contains two parts. So you will have a cation name and an anion name. So for example, sodium chloride, the cation is normally named first. There's some exceptions to this. Most of the time, there's one exception, and then the anion name is later. So with the cation name, if the cation is a metal ion, then the name of the cation is the name of the metal. So Na plus is also called sodium ion. It doesn't have like another funny name. I probably should write that there. So whatever the metal is, that's the name of the ion as well. So you just call this sodium ion. You're going to see in a second that it is a little bit different for an ion, but if it's a cation, it's a metal. Just whatever the metal is, that's the ion's name. Now, for some transition metals, I've talked about this. So if you have a transition metal, technically you only have to do this if you have multiple ions for that transition metal. But to keep it simple, just do it every time. So if you have a transition metal, when you name it, you also want to tell me the charge of the metal. So if it's Fe2 plus, because Fe is a transition metal, I would call it ion 2 ion. If I have something like copper, now copper also can have more than one valency, then the name of this ion is Cu2 ion. So if you see a transition metal, and once again you can tell by locating the element on the periodic table, you need to make sure to include a Roman number to indicate the charge of the ion, because it doesn't follow the octet rule. So without indicating in the name, it's very difficult. Well, it's almost impossible to tell what the charge of the ion is in that scenario. Some cations may be polyatomics. So if you have a polyatomic ions, just check the name of the polyatomic ion table for now. So the only one I think that you can see in the polyatomic ion table is NH4 plus, and this is ammonium ion. It's the basic, well, not the basic, sorry, it's an acid. It's the acidic version of ammonia, which some of you might have heard of, NH3 ammonia. We'll talk about that a little bit in Unit 2. So that's a cation name. Now with the anion name, it's a little bit more complicated. It's not that complicated, just a little bit. So if the anion is monoatomic, which means that if it contains only one atom, then the name of the ion is the name of the element, and then you have to end with IDE. Here are some examples. So if I have Cl minus, this is a monoatomic anion. It has one atom and it's the minus, so it's an anion. So the name of the element is chlorine. This is the name of the element. So when you name the ion, you have to change the ending to IDE. So it become chloride, which is why the name of NaCl is sodium chloride and not sodium chlorine. So chlorine is the name of the element, but chloride, so end with IDE, is the name of the ion. So if I have something like I minus, the name of the element in the periodic table is iodine. So this is iodide. So you have to end with IDE. You still can have things like O2 minus. So this is oxygen is the name of the element. So oxide is going to be the name of the ion. N3 minus. So nitrogen is the element name, but you have to end with IDE. So it becomes nitride, IDE. Okay, so that's if the anion is monoatomic and the name with IDE. If the anions are polyatomics, then again, I'm making it a bit simple for you, but you can just check the name on the polyatomic table for now. So you see a lot of polyatomic anions compared to cations, only one. So for example, PO43 minus is phosphate, and then you can have other things like CO3 2 minus is carbonate. There's a little bit of a rule here, but I don't expect you to know, honestly. So that's fine. You just need to know to convert the name of the monoatomic one to end with IDE. For these, just check the table. So you can have nitrate, for example. Okay. All right. Let's go through these questions. So when you name the whole thing, just name the cation and then name the anion. So the cation, this is an element. This is a metal. The element is magnesium, so the name of the cation is just magnesium. And this is a monoatomic anion, and it comes from, hopefully you can tell, bromine. So it's going to be called magnesium bromide. So you end it with IDE, okay? Part B, so once again, we'll name the metal first, and then we name the non-metal. Now, you kind of need to do some work here because hopefully you can tell that this is a transition metal. So I have to indicate the charge of the ion. And how would you know what the charge is? And this requires a little bit of working backwards. So the other ion is chloride, and chloride is in group 17 of the periodic table, which means that chloride is going to form a Cl minus ion because it is going to gain an extra electron to get a full shell. So each chloride ion has a charge of 1 minus. And the fact that the formula gives you 3 chloride for every ion should indicate that the ion should be Fe3 plus, which means that in the name, you have to indicate a 3 to show that that is the charge of ion in this compound. Because iron is a transition metal, you need to indicate the charge of the metal ion in the name for me. This is the only example that I think you need to know that is actually an ionic compound, even though it doesn't contain any metal. So this is one of the exceptions that I mentioned earlier. So recognize that NH4 is ammonium. This is a polyatomic cation that you can find in that purple table. So this is ammonium. And NO3 is a polyatomic anion, also in that table, which is nitrate. So ammonium nitrate is the name. You don't have to do anything else. It's pretty straightforward. So copper, SO4 is also a polyatomic ion that you can find in that table. Is sulfate. Okay. Now, once again, you're going to need to tell me what is the charge of copper in this case, because copper is a transition metal. So from that polyatomic ion table, hopefully you can identify that SO4 has a charge of 2 minus. And the fact that there is 1 copper for every SO4 means copper must be 2 plus. So I'm going to put a 2 in the name. All right. I'm going to ask you to do the rest yourself, and then we can correct it next lesson. So try E, F, G, and H. And let's talk about 4.5. So 4.5 is the last skill, is when I give you the name, and then you have to give me the formula. So in the previous one, I give you the formula, and you need to tell me the name. In 4.5, can you write the formulas from the name? Now you can write these rules now, but I think you probably have come across them in the past. Essentially, ionic compounds are electrically neutral, so the total number of positive charges on the metal ions must equal total number of negative charges on the non-metal ions. So in other words, all the positives have to cancel out all of the negatives. When you write a formula, the cations is generally placed first and the anion second. I will give you the one example that when the anions actually placed first. So this is sodium ethanoate, and we actually put the anion first. There is a reason for that. Is there a reason for that? I mean, it looks a little bit better because the anion is CH3 COO minus. So the negative is actually supposed to be at the very end of this really interesting molecule. And then Na plus is here. So we kind of put the sodium where the negative originally is so that it doesn't look like the sodium is bonding to this carbon. It's actually supposed to be attracted to this oxygen here. So this is the only one that you need to know. Any ethanoate salt, really. The ethanoate is normally written first in the formula and then followed by the cation. But for every other example, the cation is placed first and then the anion. So probably should write exception here so you know what it is. Okay, so let's talk about the steps for writing the formulas of ionic compounds. A lot of this I think people can do intuitively, but I'll give you the steps anyway if you're not sure and you need a little bit more support. So the first thing I need to give you is the name of the ionic compound. So potassium nitrate, for example, and the question is, can you write the formula for potassium nitrate? So step one is to write out the cations and anions and their charges. If a polyatomic ion is used, put brackets around the atoms. So from the name, I can tell that the cations is K. I'm going to put the number as well. So it's K plus or K1 plus. How do I know it's K1 plus? Potassium is in group 1 of the periodic table, so I can use the octet rule and predict that it will lose 1 electron to get a full shell. Nitrate. Nitrate is a polyatomic ion that you can find from the polyatomic ion table, and the formula is NO3. So it's a polyatomic ion. I'm going to use brackets around the atoms, and the charge is 1 minus. Okay, so that's step one. Write out the cations and anions and their charges. So step two is to swap the charge value of one ion to become the subscript of the other ion. So the actual formula is going to consist of K and NO3. What I'm going to do is I'm just going to put this one here. So the charge of one ion becomes the subscript of the other ion. Well, you can just use logic and you probably can get to the same answer. So if in this case, it's very simple because they both have the same numerical value of 1. So it's just Ku1, NO3, 1. And then step 3 is to write the actual formula. So there are a couple of things to just keep in mind. If the cations and anions have the same subscript, then you can simplify that to 1. If it is only 1, then you don't have to write the subscript at all. So the final answer is just KNO3. So you can drop the 1 because this already indicates, like even in this formula, without writing the 1, you can tell that it is 1. Okay? Let's go through another example. I actually think we have a few here. I might only do like half and you can do the rest. Or maybe do all of them, we'll see. So step 1, write out the cations and anions. So silver 1, they actually tell you that the charge is 1 plus because silver is a transition metal. So I don't expect you to be able to work out what the charge of the metal ion is at this point. Chloride is in group 17. It's from chlorine. So it is going to gain 1 electron and from a 1 minus ion. So if you really want to follow the rule, I mean, you probably don't have to do it for this one, but you can just swap the subscript. So it's 1 and then 1. It's pretty boring actually. And then the final answer is AgCl, silver chloride. Very commonly used substance. You're going to see it a lot in unit 2. All right, sodium sulfate. I think things are getting a little bit more interesting. So sodium is the metal in group 1. So it's going to form a 1 plus ion. So this is Na1 plus. Sulfate you can find from the periodic table. Sorry, not periodic table, this polyatomic ion table. It has a charge of 2 minus. So if you swap the subscript, you swap the charge to become the subscript, you're going to have Na2 SO4 1. And if the subscript is 1, you don't have to write it, so just have Na2 SO4. Okay. Magnesium hydroxide. Magnesium's in group 2, so Mg2 plus. Hydroxide is a polyatomic ion. You can find it in the tables, OH, and the charge is 1 minus. So if you swap the charge for the subscript is Mg1, OH2, and then you tidy it up, just MgOH2. So you don't have to write the subscript if it's 1. Zinc nitride. Okay, so zinc 2 is a transition metal. So zinc 2 plus. Nitride. What's nitride? Nitride is NO2. Is it minus? NO2 minus? 1 minus? I might have made that up. I can't remember. But I think it is right. Anyway, so you're going to swap. So zinc 1, NO2, 2. And then if the subscript is 1, you don't need to write it. So this is the final answer. Okay. Do we have any more? Aluminium phosphate. Not that exciting actually. Aluminium is in group 13, so it's going to form a 3 plus ion. Phosphate is a polyatomic ion, so PO4, 3 minus. So if you swap these, you have Al3, PO4, 3. And because I don't think we have had an example like this, but if both the cations and anions have the same subscript, then you can simplify them to just AlPO3. Okay? Sorry, PO4. Is that the last one? Ammonium carbonate. All right, slightly interesting. Ammonium is 1 plus, NH4, 1 plus. Carbonate is also a polyatomic ion, so CO3, and then the charge is 2 minus. So if you write the formulas as NH42, so the charge of carbonate becomes the subscript of ammonium, and then CO3, and then that just a 1, and then you can simplify. Please don't open the brackets, by the way, this is not math. So you're trying to show that there are 2 NH4 plus ions, and you're not showing this N2H8. So please don't expand the bracket and multiply things out. That doesn't make sense. So that's the final answer. So it's the last one. Oh, it's not. Oh, this is the last one, I think. So magnesium, again, Mg2 plus. It's group 2, the periodic table. Hydrogen sulfate. I don't remember what hydrogen sulfate is. I think it's HSO4 minus. Okay, let's just go with that. Mg, so 1 minus 1, HSO4, 2. So you have MgHSO4, 2, and that's the final formula. Is that the last one? Yes, that is the last one. All right, so that's it. I have a little task for you. Maybe I'll show you what the task is. So the task is to sort some cards. So you have a Jamboard activity. The Jamboard contains some cations. So you have some cations, some anions, some subscripts, the ion formulas, and the names, the cation names and the anion names. So your job is to put the correct cards in the correct spot so that it forms a proper row. So basically, say for example, Fe3, and then the subscript for that is 2, then you have SO4, subscript is 3, and then that will give you Fe2, SO4, 3, and then the names iron 3 sulfate. So you should be able to pull things in and out. You might have to shrink some of the cards so that they fit nicely into the table. There should be enough cards to fill all these blanks. So your job is just to try to figure out which card goes where. And once you're finished, make sure you submit it on Google Classroom. And then I think I have some homework textbook questions. If there's any question, email me, all right? Other than that, thank you. See you next week for sure. Well.